our story of acids and bases with a curious thing that happens to a particular kind of chemical, which is called either a metal oxide or a non-metal oxide. These particular chemicals do something very interesting when we put them in water. They turn into basic or acidic solutions, and so they're related to acids and bases in general. So we're just going to examine what happens to these, and we'll start with the metal oxides. And first we'll talk about what metal oxides are. Basically, it's a metal that combines with oxygen gas, and it produces what we call a metal oxide. So I'll give you an example. Magnesium is a metal. If we combine that with O2, oxygen gas, then we end up with MgO, which we call magnesium oxide, metal oxide. So the metal can be anything, and then the oxygen, of course, is the oxide. And of course, they need to be balanced like any good equation. So we would have to make two of these and two of those to use up the oxygens in the O2. Remember, oxygen is always O2. It's never O by itself. All right, so there's an example of a metal oxide being produced right here. Another example of a metal oxide is something, let's say, iron. And there's two ways that iron can combine. It can combine in this form, Fe2O3, which we would call iron 3 oxide. Remember, multivalent metals have more than one way of combining. And the other option would be iron combined with O2 to form this compound, FeO, which is called iron 2 oxide. Remember how to crisscross and get those two formulas. So some metals form different oxides. Any metal can do this. Silver, tin. There's one metal, or there's a few metals, I guess, that don't react very well with oxygen or don't seemingly react at all. Gold, for instance, doesn't do this. It doesn't react with oxygen, and that's because it has a different electron arrangement that doesn't find this reaction very favorable. In other words, it doesn't produce a more stable outcome. So we don't see gold oxides. Often we don't see platinum oxides either. I mean, we can force these reactions to happen if we use extreme amounts of heat and extra energy, but typically under normal conditions, they don't rust. That's what we call this, by the way. Oxides are called rusts, or sometimes we use the word tarnish. Silver tarnish is silver oxide forming on the outside of some piece of silver because, of course, it's exposed to the oxygen in the air. Iron exposed to oxygen in the air produces this rusty, orangey red colored powder, which is primarily iron 3 oxide. Iron 2 oxide is a little redder, and it can be produced as well, but typically this one is the more common one that we see under normal circumstances. These are all oxides of metal. We don't like them because they don't look as pretty. Another example is copper. Right? Copper can form oxides. If we take the metal of copper, it produces this metal, which is copper 2 oxide. Right? Copper 2 oxide, which is what makes it's actually a greeny color, a very pale green color that we often see on rusty pennies. Pennies that get rusty turn that weird green color. You can also make copper 1 oxide, copper being multivalent. Copper 1 oxide looks like this. But copper 2 oxide, this green color, is quite common. Sometimes fancy buildings use copper on the roof, and the roof turns green. So if you see a building with a green roof, it's probably got copper sheeting on the roof. Now, what's interesting is that in some cases, this rust or tarnish can actually protect a metal. If you think about the surface of a metal, let's say it's copper, well, if it starts to rust, there's oxygen here in the air above the metal. And so it's reacting slowly and forming a layer of this greeny colored rust on top. But if you let it rust completely on top, the copper oxides that form, copper 2 oxide in this case, form a barrier. And now the oxygen can't get to the metal underneath because the rust has formed a protective barrier. And it will stop tarnishing or rusting. This is convenient because it preserves the metal. So as much as we don't like the color or the look of it, it's still preventing further oxidation. If you polish this by taking a chemical that removes the oxide, the copper oxide, or silver oxide, if this is your nice silver, now you've exposed the metal and it will rust again. And each time it rusts, it takes away, you're taking away the silver, right? Because or the copper, as you remove the copper oxide, this copper that's in it is going with it. And eventually it'll completely be gone. So tarnishes and rusts and things are usually if something does this, we call it a tarnish. If it forms a protective coating. Rusting metal, iron, up here, is a little different in that it corrodes and rusts sort of in a different way. The rust doesn't form on the surface. It sort of eats away at the metal and works its way underneath like this. And so it doesn't form a protective layer because it just basically keeps on going, see? And it rusts like making a hole, rusts right through. So this is why you see iron rusting away completely. It's a different little chemical reaction. But we don't need to worry about those details. We just need to understand that any metal that combines with oxygen can produce an oxide, a metal oxide. Now what we want to do is look at what happens when we put a metal oxide into a solution of water. Oops, what did I do there? Here we go. Draw a line. Let's look at a metal oxide in water. So we use the magnesium oxide as our example, right? We'll take magnesium oxide. So first, I'll write this equation. Here's how we produce the magnesium oxide. There's the reaction that produces the magnesium oxide. Now let's take this product and let's put it into some water by combining it as MgO plus H2O, and let's see what happens. Well, if you put MgO in water, we know what happens when things go into the water. Water tends to be able to tug on things. So I'm just going to draw a couple of pictures over here on the side. I'll erase them in a minute. But remember that water is polar. And by polar, what we mean is that the electrons are spending more time around the oxygen than they are around the hydrogen, creating these two poles, negative and positive, sort of along this axis. So the O side of water is negative, and it pulls on positive things, like positive ions. And the H side of water pulls on things that are negatively charged. So if we look at this, we can see that what it is it's composed of magnesium ions, which are positive, and oxide ions, which are negative. And the water can pull these apart. And we've seen that a magnesium ion can be pulled away from its oxide in this case, and it would be surrounded by water molecules, sort of like this, dissolved in the water. This is what we say is dissolved in water, right? And it's sort of held apart from the O. Now the O over here, I'll put the O here, it's a 2 minus. If water comes close to O, something interesting happens. Here the H's would be attracted. The H side, which is the positive side, would be attracted to the negative ion that's been sort of separated from its magnesium. But this O2 has such a strong pull that not only does it get separated, it can literally grab one of these H's nearby and pull it over to itself. And when it does that, what you end up with now is an OH minus and another OH minus over here that got its hydrogen taken away from it. And of course the other waters remain unaffected. So they would still sort of be hovering around here like this. And so you see what happens when this oxygen gets pulled apart in the water, it does an additional thing of pulling this little H over, and it produces two hydroxide ions. The original oxygen grabs an H to become this hydroxide, and it leaves behind this one that it stole from and produces two hydroxide ions. So we can actually then see what would happen. What we would actually get is, on the other side of this equation then, a magnesium ion. Let me just erase some of what I've drawn here and finish this equation. We would get a magnesium ion, a 2+ ion, that is over here, sort of surrounded and dissolved in the water. So we write AQ. Remember the little AQ, that's what that means. And then over here, we would get an O surrounded by water like this, but instantly it would do this, and it would turn into two hydroxide ions, which are also sort of surrounded by or dissolved in the water. And we get this interesting scenario. Now you'll notice that we still are balanced. We haven't lost or gained anything. It's just a reaction where a hydrogen has been transferred from the water molecule to the O2 oxide ion, the O2 minus oxide ion, right? That's been released as the original metal oxide dissociates. And so that's how we could look at this. We could look at it, a shortcut for this. If you recall, there's a way we can shortcut writing this. We simply write magnesium hydroxide AQ. Remember, that's what AQ means. It means the ions are pulled apart. So we could write an overall reaction like this. Magnesium oxide plus water, right, will produce Mg, magnesium hydroxide, in its dissolved AQ state, which means to the chemist that in your brain, in your little thought bubble, when you see this top thing here, what you think of is Mg2 plus surrounded by water and hydroxide ions surrounded by water. There'd be two of them here, right? Those mean the same thing, these two things. And that's what happens to a metal oxide. The same would happen to any other metal oxide. Iron oxide would become iron hydroxide, either iron 3 hydroxide in most cases, or iron 2 hydroxide, depending on which one you used, right? Remember, we had all these possible. Copper could produce copper 2 oxide, which would then become copper 2 hydroxide in the water, and copper 1 hydroxide in the water, okay? And it's the same idea. The only difference at all is just over here. This little guy would be a different metal. But all the other stuff that happens is the same. And so it's interesting that we produce hydroxide ions. And what do you call a solution that has hydroxide ions in excess? We call it a base. And so a metal oxide will produce a base because it produces an excess of hydroxide ions. But it's important not to just memorize this little formula. Don't just memorize this as a bunch of symbols and numbers. Try to see this picture or this story of what's actually happening so that you understand what's going on underneath the equations. Okay? And remember what this little powerful AQ symbol actually means. Okay, let's now look at, say, a non-metal oxide, which is a different story altogether. So just like a metal oxide is a metal plus oxygen, well, you can guess that a non-metal oxide is some non-metal combined with oxygen. Non-metal plus O2, and it will produce what we call a non-metal oxide. Now, these ones are a little trickier because other things can be involved. So I'm going to start with some of the simplest ones so that you can see how they work, and then I'll show you a couple maybe of the more complicated ones. So let's take a non-metal oxide. Well, carbon's a non-metal. So if we take carbon and we combine it with oxygen, O2, well, guess what we can produce? Carbon dioxide, CO2. Now we can also produce other carbon oxides like carbon monoxide. But we're going to ignore that one for now, and we're going to use this example just because it's a little simpler for understanding. So here is a non-metal oxide. We call it carbon. And of course, because they're non-metals, we have to use the prefixes, right? Dioxide, because there's more than one option. There's only one way to get magnesium oxide, but carbon has a couple different oxides it can form. Carbon monoxide, carbon dioxide, and so we use the prefixes for non-metals. But it's still an oxide of carbon. It's a non-metal oxide. All right. Another example would be nitrogen. If you add nitrogen to O2, you can get nitrogen dioxide, NO2, which is also a metal oxide. So there's lots of different metal oxides, non-metal oxides you can get. You could also have nitrogen combined with O2 to produce a different metal. For instance, maybe N2O5. Nitrogen has lots of different oxides. N2O5 would be called dinitrogen pentoxide. Pentoxide, dinitrogen pentoxide. Okay, and of course you'd have to balance this equation. It's a little bit tricky because you've got to have your O's working out here, and you can see how the O's are weird. If we put 2 here and make 10, we can put a 5 here and make 10 oxygens, right? And then our total is 4 nitrogens, and we can put a 4 here. So it's a little harder to balance, but that's another possibility. So because there's more than one option, we get a little more complex chemistry going on here. But let's look at what some of these might do if we were to take this carbon dioxide, or maybe this dinitrogen pentoxide, or even this nitrogen dioxide. What would happen if we put those in water? Those are the non-metal oxides. So let's put them in water and see what we get. Let's take, for instance, carbon dioxide and put it in with some water, H2O. Well, you can kind of look at all the atoms involved here, and you can imagine if this little carbon dioxide here just kind of goes over here and sticks itself into there, you'd have H2, and then you'd have CO2, but then you'd have the other O, which would make it CO3. And we recognize this chemical as carbonic acid. Carbonic acid, which means the non-metal oxide, when it dissolves in water, or reacts with water actually, it actually produces carbonic acid. It produces an acid. Remember, the metal oxides made a base because they produced excess hydroxide. This produces an acid. And remember, this would be an aqueous solution because it's happening inside water. And remember that that's a shortcut. Aqueous is a shortcut for the H's being sort of pulled away, the H pluses, and the carbonate being separated from each other by the very same process that, of polar water pulling on the ions, which produces this effect. So this is just a shortcut for that. But also remember that these H pluses don't like to float around. They tend to ride on a nearby water molecule, and all this chemistry has to come back to you. An H plus sort of by itself will be attracted to one of these little spots here on the water molecule that is typically not being shared, but it will form a coordinate covalent bond, and we'll get an H3O plus. So what this very quickly becomes is the hydronium ion and carbon. Oh, I forgot to put the charge up here, the 2-. I better fix that. And of course, these are both AQ, and there'd be 2 of these. So the H plus actually hitches a ride on a water molecule, and it produces hydronium, which is sort of the symbol or the thing that we recognize. If it's in excess, it produces an acidic solution, right? An acidic solution. So this is producing carbonic acid. And we could write this like I did up above, right? With the AQ right here. But we have to realize in our mind that when we have carbon dioxide, and it's reacting with water, what it's really making happen is H3O pluses in that water and carbonate ions, right? That's really the end result. And we, of course, would make two of those. Now, the balancing is tricky because when I write it like this, it's really not a proper equation. It's got ions on one side and it's got compounds on the other. But this, I'm just trying to show you that this is really what's in the cup. Okay? When you mix these together, you have to understand the story. We write it like this, with this little powerful AQ sign, but remember what that means. It means that what's really in your cup is this. Okay? And it's harder to balance because we don't account for the water molecules that this H plus is hitching a ride on, right? If we think of an H3O as just an H plus, because that's what it was if you look up here, and we ignore the molecule it's riding around with, then really that's two H pluses, which balances with the two H pluses over here, and then the CO2, there's two O's and one O, and there's the, what we have over here is three O's and four O's, right? So we're pretending this right here is an H plus, so it has no O's in it, because we're ignoring the water molecule it's riding on. That's kind of a little bit confusing. So typically we would write it this way, right? In fact, I'll write it again underneath. We would write it as CO2 plus H2O, and we would write it not like this, but simply as carbonic acid, H2CO3. And we would write AQ, which means that this is what's happening. So see, you have to understand that little AQ is a very powerful thing, and it means a lot. You can't just write it and forget about it. As a chemist, the equations describe what's going on, but you have to know what's in your cups, what's in your test tubes. And this is really what you would have if you had a test tube of carbonic acid in aqueous solution. Okay, here's another example. Let's take our N2O5, our dinitrogen pentoxide, and let's combine it with water. Well, you can sort of see that if you take N and O's and you put them together, and then there's some H's involved as well, that you're probably going to make HNO3, or nitric acid. And of course, to balance this, you would have to have, let's see, if we put a 2 here, then we have 6 O's, 2 N's, 2 H's, and everything balances out. But this would be AQ. And again, we must remember what that really looks like in the cup. It would be 2 H's, 2 H pluses that are released, right? And 2 nitrates that are pulled apart. Actually, yeah, 2 nitrates like that. So we'll put a plus there. Because they're surrounded by water. The polar nature of water is tugging on these ions and it rips them apart. But the H plus, as soon as it's ripped apart, very quickly rides on a nearby water molecule to make the hydronium ion. And so as soon as you make this, what you really have is this in your cup. Okay, but again, we write it like we've written it in the top equation. We write this equation because it's easier to balance. The problem with trying to write this in here is we have to add H2O molecule, 2 of them in fact. We have to add 2 H2Os in there to make, for these H's to ride on. And we don't really show those. 2 H2Os have to be added. We don't really show those in the upper equation. So again, this is just for your brain to think about while we write it like this, understanding that it's all because of this AQ and what that means. Now, with the nonmetal oxides, it can get a little tricky. So for instance, if we were to try to take NO2, nitrogen dioxide, and combine that with water, well, we would still make nitrate, and actually nitric acid. We could still make HNO3, my mistake. We're going to have to make 2 of them. That's why I'm thinking that. But we're going to also make something else. To make this work out, we're also going to make something called nitrogen monoxide. which is a gas that would sort of bubble slowly away. So this would be AQ, right? And to balance it, we would have to make 2 of these. We'd have to use 3 of those. And I think that gets us everything working out. If we count up our O's, we have, let's see, 6, 7, 6, 7. It all works. Everything looks good. Now, the problem is it's not easy to predict this little extra molecule here that's released in the reaction. And if you're a beginning chemist, you would know how to write this side of the equation because you would know how the extras were to fit in. So for us, in our beginning to understand these oxides, for the non-metal oxides that are simple like this, you can kind of just see them, carbon and so on, and this dinitrogen pentoxide. You notice that we didn't need anything else. All we needed was the carbonic acid or the nitric acid to make it work. We'll be using those examples more often. If we come across something like this, then I will be sure to tell you what this extra little bit is so that you can balance the equation properly and figure it out. However, the important thing to realize is that we are still making this HNO3. This little gas is bubbling away and it doesn't seem to have much effect on what's going on. Now, of course, this NO could also react with the water and produce additional nitrate. So it's almost like this could then produce more of this, right? But we won't get into all those details. We'll just pretend that this is not part of the picture. For us, we just want to remember that this will become hydronium ions as those H's are pulled apart and they ride on other molecules of water. We'll get 2 hydronium ions there, and we'll get 2 nitrate ions in our cup. These will be AQ, dissolved in the water, aqueous. So remember, this is what you have in your mind when you see this with this little magical AQ beside it. All right, so now we've seen that if we take a metal oxide and we put it into water, it will produce an excess of hydroxide ions and therefore make a basic solution. And if we take a non-metal oxide and combine it with water, it will produce an excess of hydronium ions, which is what we call an acid. And so it makes acidic conditions. A good example of this is what happens when you take pop, soda pop, and you dissolve carbon dioxide in the water of the pop. Well, the pop then contains carbonic acid, which makes the pop very acidic. It would be aqueous carbonic acid, so I'll be a good chemist and put my AQ there, but that's what it is. It's carbonic acid, and that makes pop acidic. And so it reacts very much like an acid. All right. Then what we can do is we can take sort of the whole story and we can look at, what would happen. What would happen then, a sort of a big, long story here. Let's take some magnesium oxide, okay? And we put it in this cup. Here's my cup, and here's the magnesium oxide. And over here, let's take some carbon dioxide, and let's put it into this cup, okay? All right, so if we drop these into the cups, we know what will happen. The magnesium oxide will react with the water, and it will magnesium oxide plus H2O, and it will produce, it will yield, quick, come back. It will yield magnesium hydroxide in aqueous solution, like this. Oh, I forgot a 2. Better not go too fast. I put the brackets in there like I should, but I forgot to put the 2. Let's put the 2. And what that means is that now inside this cup, remember what I said about, remember what's in your cup. We have these ions and we have these ions. And in fact, we would have twice as many of these, because if you look at the end result, there's 2 hydroxides. So that's what's floating, and they're floating around separated because of the polar water, which has pulled them apart and surrounded them. So that's what's in our cup. And there's the equation that describes it. And then over here, we have the carbon dioxide. Well, carbon dioxide plus water is going to produce carbonic acid, H2, and that would be aqueous as well. So what does that mean? Remember what that means as far as our cup. You know what I'm going to do? I'm going to make my cup a little bigger so I can write some more things in there. It's pretty small. Let's make a bigger cup. Okay, so what's in my cup? Well, the H pluses will become separated, and the carbonate will become separated. So I'll have carbonate ions, 2 minuses, floating around. Those H pluses, though, are very quickly going to ride on a nearby water molecule. They're going to form a coordinate covalent bond with the oxygen. And so I will get this in my cup. This is what's really floating around in my cup. And so then, what would happen if we mix the cups? If I pour the cups together? Well, if I pour the cups together, essentially, I'm taking this product. Whoops, I meant for that to be red. I'm taking this product from one cup and mixing it with this product from the other cup. And so you can see what that becomes. It's magnesium hydroxide, AQ, plus carbonic acid, AQ, dissolved in water. And we know that this is now an acid mixed with a base, which is a neutralization equation, which will produce a salt and a water. The H's and OH's will make the waters, and you can see how the magnesium and the carbonate will make the magnesium carbonate plus water, H2O, the salt in the water. Now, in this case, carbonates are often not very soluble. So whether or not this magnesium carbonate remains aqueous or precipitates out as a solid, to be honest, I haven't got that offhand. I'm not sure if magnesium carbonate, I think it's not very soluble. So it may precipitate as a solid, or it may stay in the solution as dissolved ions. But either way, it's sort of out of the picture. It's not really playing any role in the neutralization, right? And of course, we'd have to be careful to balance this equation as well. But let me have a look here. I think we're going to make 2 waters, right? So we should balance it like this. And this water will become a liquid. All right. So usually when we have these, we end up with aqueous salts that remain dissolved, but sometimes they can precipitate out as a solid too. So we won't worry about that. What we have to understand is that they're not part of the reaction. They're not part of what's actually going on. So now what we can do is we can write what's actually in the cups. Okay? To understand, again, we're going to use the Ionic Equation, and I'll write it in green so that it's not going to be confusing. So we're going to show what this AQ means. This AQ right here means that everything is going to be pulled apart. So this is going to produce magnesium ions. And then the hydroxides will be pulled apart as well. So all of these need AQ beside them in the water. And then, of course, this will produce H pluses. These H pluses will be released or separated, dissociated, we say. But they will very quickly ride on another water molecule that happens to be nearby and produce the hydronium ions. They'll make 2 of those. So really, remember with acids and bases, H3O plus is really just the H from the acid, but it's riding on a water molecule, so it just looks a little bit different. And then we'll have a carbonate ion here with a 2 minus. Oh, this is AQ. This is AQ. Everything here will be AQ. Now on this side, like I said, we're not sure if the magnesium carbonate is going to solidify as a precipitate and fall out of the solution, or if it's going to stay as ions in the solution. But for now, I'll just draw it as ions anyway, because if it does precipitate, it would precipitate after these ions are formed. So let's put CO3, 2 minus, AQ, and then our H2O. And of course, we'd have 2 of those H2Os. You've got to carry these numbers down, right? So this sort of represents the ionic equation, understanding that this part may be a precipitate or it may be remain dissolved in the salt. However, either way, those are spectator ions because they're not changing. Whether you are dissolved or whether you're precipitated, you're still an ion. You're still magnesium 2+, and you haven't changed in any way. And so you're what we call a spectator ion, which means you're not doing anything. And then here, of course, we have our good old 2OH minus AQ plus 2 hydronium. So that's 2 hydroxides plus 2 hydroniums. And we see we make 2 waters. And this is the essence. This can be reduced. We don't really need the 2s for the simplest ratio. And so we can see that we get the classic neutralization equation of what's really happening in the cups. And that is that the base is making hydroxides, the acid was making hydroniums, and they're going together and they're making water. And the end result of mixing these solutions is basically just neutral water with no excess of hydronium or hydroxide. And just one more thing to review, it's always good to review. Water has no excess hydronium or hydroxide, but don't forget the water dance. Water itself does produce or sort of dissociates into H3O pluses and OHs, right? And I should have drawn an arrow that goes both ways because this is a back and forth reaction. This water dance is happening all the time. And remember, you've got a water here and another water happens to come by, and this little H gets pulled over here, producing a hydronium, an H3O plus, and leaving this OH minus behind. But you're making one of each. There's no excess. And instantly, this H3O plus will find another hydroxide that has been made by 2 other water molecules, and it will rejoin. These will come back together, and they'll make an ordinary water again. So that's the backwards version. And this little dance is always happening inside water, back and forth, in what we call a dynamic equilibrium. But the key is that this and this are never in excess. They're always averaging out to the same amount of each. And that's what we mean by a neutral solution. You need to have excess hydronium for an acid or an excess hydroxide for a base. And of course, if we go back here, that's what we had. In our metal oxide, here's our excess hydroxide that comes from the magnesium oxide, right? And here's our excess hydronium coming from the carbon dioxide rather than from the water itself. The water dance, I like to call it. So there, we reviewed just about everything that we've covered in the acid-base unit by looking at metal oxides and non-metal oxides. Remember, a metal oxide will make a base with hydroxide, and a non-metal oxide will make an acid of some sort, which produces hydronium ions.